Hello, good morning everyone. Welcome back to Vichamandra online classes. So yesterday we have discussed the organic chemistry, in that the basic concepts required to understand the organic chemistry, well, in that the classification of organic compounds and how to identify the hybridizations of the carbon and natures of the carbons and hydrogens. Based upon the nature, types of carbons and hydrogens, yesterday we have discussed. Now today let us be entering into the topic. That is what the main topic is, hydrocarbons. So let us be start. Hydrocarbons. So if you see the hydrocarbons, yesterday we discussed two types of hydrocarbons: saturated hydrocarbons, unsaturated hydrocarbons. Today we are going to discuss the saturated hydrocarbons. Saturated hydrocarbons. Saturated hydrocarbons, under this, what comes under saturated hydrocarbons? Alkanes. Alkanes. The general formula for the alkanes is CnH2n plus 2. CnH2n plus 2. And remember that here the suffix name is ane, methane, ethane, propane, butane. Likewise, the suffix is ane. Remember that. And the simplest alkane, that we found, what is that? Methane. The simplest alkane is methane. That is a one carbon containing alkane, that is a methane. See, this methane also we call it as marsh gas. Marsh gas, because of abundance of this methane in marshy places. Marshy places means very wet areas. Marshy places, we are calling this methane as marsh gas. And the other name of alkanes, what is the other name of alkanes? Alkanes also we call it as paraffins. Paraffins. Why we are calling them as a paraffins? Because of their less reactive nature. They are less reactive at room temperature. At room temperature, they are less reactive. That is why we are calling them as paraffins. Next one, in alkanes, each carbon, if you take any alkane, each carbon undergoes sp3 hybridization. Every carbon undergoes sp3 hybridization, and the percentage of S character, you see, percentage of S character, that is 25% of S character and the 75% of P character. And in alkanes, there was only C single bonds only present between the two carbons, only single bonds. And if you see the CC bond length, carbon bond length, if you measure, that value is equal to 1.54 angstroms. 1.54 angstroms. So this is what CC single bond length, 1.54 angstroms. And if they undergo the sp3 hybridization, what is the geometry? So here they orient in tetrahedral geometry. Tetrahedral geometry. In tetrahedral geometry, what is the bond angle? So the bond angle is 109 degrees. That is the bond angle. So this is what general introduction about. So about So that is a general introduction about the hydrocarbons. Let's move to the IUPAC nomenclature. So how to give names to the alkanes? IUPAC nomenclature. And if you see the skeleton of IUPAC nomenclature of alkanes, it has prefix. The skeleton for IUPAC now prefix, root word, and suffix. So this is the IUPAC skeleton for alkanes, prefix, root word, suffix. What the prefix indicates? Prefix always refers what? Substituents. So if there was any substituents, and that substituents we represent as prefix. Okay, again, prefixes are of two types: primary prefix, secondary prefix. Primary prefix. So primary prefix, this is what secondary prefix. Secondary prefix always indicates what? Substituents. Primary prefix always indicates what? Whether it is a cyclic or acyclic. Cyclic or acyclic. So two types of prefixes: primary prefix, secondary prefix. So primary prefix, if it is a cyclic compound, we use the primary prefix as cyclo. If it is a acyclic, we won't use any primary prefix. So two types of prefixes are there: primary prefix, secondary prefix. Here we are discussing alkanes. That is why there was not necessary of primary prefix. We won't only consider secondary prefix, substituents. And what the root words? Root word indicates number of carbon atoms. In main chain. Main chain also we call it as parent chain. So in the parent chain, how many of carbon atoms are there? That we represent as a root word. So as we know, the number of carbons in parent chain is 1. So what is the root word? Meth. So 2, eth, 3, prop, and 4, but, 5, pent, 6, hex, 7, hep, 8, oct, 9, non, 10, dec. So likewise different root words are there. These are the different root words we use. Okay, based upon the number of carbons. Next, suffixes. As like prefixes, suffixes are also two types of there: primary suffix, secondary suffix. Here, primary suffix indicates primary, secondary. Primary indicates what? Nature of bonds. Nature of CC bonds. Whereas secondary prefix indicates functional group present in it. Functional group present in the given organic compound. See, primary, nature of the CC bond. Suppose if the CC bond is only single bonds, so what is the primary prefix? Primary suffix? A. CC double bond is there. What is the primary suffix? In. And CC triple bond is there. Then what is that? Ein. So in, ein. These three are what? Primary suffixes. So in case of alkanes, we will use primary suffixes only. The secondary suffixes we use only for the compounds having functional groups. There was a different secondary suffixes for the different functional groups. So we are not discussing here. We are discussing only about the alkanes here. Okay. Next. Let us move to the discussion of nomenclature by taking few examples. Now I'm starting with a straight chain hydrocarbon. Straight chain hydrocarbon. Let us see. So that is a CH3, CH2, CH3, CH3, CH2, CH3. So in this case, here there was no substituents, so there was no prefix. Let us restart with the root word. What is the root word? 1, 2, 3. So total 3 carbons in the main chain. So the root word is pro, and between the carbons only single bonds are there. So A, pro plus N, propane. Pro plus N, propane. That is the name of this one. Similarly, you take one more example, that is CH3, CH2, CH2, CH3. Here in this case, total here also no substituents, no prefix. Let us restart with the root word. What is the root word? Total 4 carbons are there. For 4 carbons, root word is but and suffix is ane. So the name is but plus ane, butane. So likewise, we can easily give the names to the straight chain hydrocarbons. It is very easy. Coming to the branched chain hydrocarbons. Branched chain. So for the branched chain hydrocarbons, we have to follow some rules. So what are the rules we have to follow? The first rule is longest chain rule. Longest chain rule. What is this longest chain rule? So according to the longest chain rule, if the compound having, for example, you take this example. So likewise, a compound they have taken. Here how many branches are there? 2 substituents are there. 2 substituents. So now we have to follow according to the longest chain rule. Thus, the chain which is having large number of carbons, we have to consider it as main chain. See, if you take this chain, the straight chain, this one, how many carbons are there? 1, 2, 3, 4, and 5. Only 5 are there. But if you take this one, how many carbons are there? 1, 2, 3, 4, 5, 6 carbons are there. Okay, so which chain has large number of 1, 2, 3, 4, 5, 4, 5? But 1 second, there was a mistake. Five, 6, 7 carbons are there. Total 7 carbons in the main chain. So according to the longest chain rule, the chain which is having large number of carbons, we have to consider as a parent chain. As per that logic, so as per that logic, this is the main chain and this is not the main chain. Okay, so this is a main chain. Now what are the substituents? This one is a substituent and this is another substituent. 2 substituents are there. So likewise, we can differentiate the substituents present in the parent chain by following what? Longest chain rule. It's very important rule. Next, move to the second rule. What is the second rule? So after we differentiate the differentiate the compound into substituents and parent chain, immediately we have to start giving the numbering. Okay, so for giving the numbering, we have to follow lowest number rule. Lowest number rule. What is this lowest number rule? So let us explain. Let us discuss this with by taking an example for this. Here I am taking an example. I am taking only carbons. Don't be confused. Okay, so this is a single substituent. Only one substituent. So this is a parent chain and this is a substituent. Okay, now after we differentiating into parent chain and the substituents, immediately we have to give the numbering. So numbering you can give in two ways, A and B. A means you start giving the numbering from left to right. That is 1, 2, 3, 4, 5. Okay, in the second case, you start giving the numbering from right to left. 1, 2, 3, 4, 5. Okay, so as per the lowest number rule, the numbering where the substituted carbon, so this is the substituted carbon. So the carbon on which the substituent is present, that is what we call the substituted carbon. So the substituted carbon number should be least. That is the correct number. See, as per the A, on which carbon substituent is present? Fourth carbon. As per the B, the substituent is present just in second carbon. So B is the correct numbering, A is wrong. So understood? So as per the lowest number rule, the substituted carbon should be what? Should be less. So that is what we call it as lowest number rule. Next, move to the third rule. So after we differentiate them into, after we successfully give the numbering, we have to first give the name. We have to start with the substitutes. In case of presence of many substituents, more than one substituent of the same type, so only one category. So in that case, not necessary to mention them many times, just mention them at a time, simply by mention their positions. For example, take an example like this. Okay, so likewise I have taken a compound. So what is a parent chain? This is the parent chain, and these are what? Substituents. Total 3 substituents are there. One carbon containing substituent, that is called methyl. So in case of presence of many substituents of the same type, so here total 3 methyl groups are there. 1, 2, 3. All 3 substituents are same methyl groups are there. In that case, so after we differentiate in the next, what we need to give? We have to do the numbering. So 1, 2, 3, 4, 5, 6. Here, if you give the numbering from left to right, so in case of presence of more than 2 or more than one substituents, now what we have to do? We have to add the numbers where the substituents are present. Okay, tell me on what carbons the substituents are present? Second carbon, third carbon, and fifth carbon. You take these numbers: 2 plus 3 plus 5. So what is the total value? 10. The sum of all this is 10. If you give the numbering from right to left, 1, 2, 3, 4, 5, 6. If you give the numbering from right to left, in that case, at second carbon, at fourth carbon, and at fifth carbon. So what are the positions? 2 plus 4 plus 5. So what is the total value? 11. Which is the least value? 10 is the least value. So this is the correct, and this numbering is wrong. So that is according to the lowest number. Okay, this is the correct numbering. So in case of presence of similar substituents, many similar substituents, just to mention the positions where they are present. Okay, tell me what are the positions the methyl substituents are present? At second position, at third position, and at fifth position. So I'm writing here 2, 3, 5 hyphen 2, 3, 5. How many times it was repeated? 3 times. That is why trimethyl. So prefix is over. Now what is the root word? Root word. How many carbons are there in the parent chain? 6 carbons. So hex and the suffix is A. So 2, 3, 5 trimethyl hexane. And remember one point, when you are writing the name, in that name there was a numerical like 2, 3, 5 likewise, and a word. A numerical should be separating from the name with a hyphen. You must mention the hyphen between a numerical and a word. That point you have to remember. So this is what third one. In case of presence of 2 or more than 2 similar substituents. Okay, not necessary to repeat it. 2 methyl, 3 methyl, 5 methyl likewise. Just mention where the position, which positions of methyl groups are there. 2, 3, 5 hyphen. How many times it was repeated? 3 times. So trimethyl. Suppose if it repeated 2 times, di. 3 times, tri. 4 times, tetra. 5 times, penta. Likewise, you can use Latin words here. This is what third rule. Next, move to the fourth rule. What is the fourth rule? That is the equivalent rule. Equivalent rule. And as per this equivalent rule, let us take an example. Okay, likewise, I have taken an example. Okay, so this is the example I have taken. So what is the parent chain here? The parent chain is, this is the parent chain, and here 2 substituents are there. 2 substituents. And after we differentiate them into substituents and parent chain, next what immediately we have to do? We have to do the numbering. You give the numbering from left to right. If you give the numbering from left to right, 1, 2, 3, 4, 5, 6, and 7. So at what positions the substituents are present? 3 and 5. So 3 plus 5, that is equal to 8. Now give the numbering from right to left. 1, 2, 3, 4, 5, 6, and 7. Here also third and fifth position. 3 plus 5, that is equal to 8. So in case of presence of different substituents at the same locations. Okay, so then we have to follow equivalent rules. So equivalent positions. See, if we get the same numbering, the sum of the 2 numbers remains the same in both directions, then those 2 positions we call it as equivalent positions. So what are the equivalent positions? Equivalent positions here. See, second position and sixth position both are equivalent. Why? Because 2 plus 6 to 2 plus 6 both are equivalent. Similarly, third and fifth, they both are what? Equivalent positions. So in case of presence of different substituents at the equivalent positions, then we have to follow alphabetical rule. Alphabetical rule. As per the alphabet, see, this is what is the name of this one? Ethyl group. This is ethyl. And what is this name? Methyl. This is methyl. So as per the alphabet, which first letter will come? See, E will come first in the alphabetical series. So this ethyl group containing carbon should get the least number. So this is the correct number. This is the correct number. So the second one is wrong. So in case of presence of different substituents at equivalent positions, you follow this equivalent rule. Next one. Next one. In case of presence of different substituents, presence of different substituents. Then what we have to follow? We have to follow alphabetical rule. alphabetical row. I will give you an example to explain this. That is, so likewise, what happened here? This is the parent chain, and then substituents. Three substituents are present. Three substituents. What are the three substituents? Two are the methyl groups. One is what? Ethyl groups. All the substituents are not same. Okay. Then do the numbering. If you do the numbering from left to right, third position, fourth position, sixth position. 3 plus 4 plus 6. So total value 13. If you do the numbering from right to left, second position, fourth position, fifth position. Second position, fourth position, fifth position. How much? 9 plus 2, 11. So which is the least value? 11 is the least value. So the correct numbering is, this is the correct numbering. This is the correct numbering. Okay. Now, after you do the numbering, you start giving the name. Okay, substituent, three substituents are there. But 2, 3 are different. See, methyl, ethyl, two different types of substituents are present. In that, ethyl will come as per the alphabetical order, and that ethyl group is presented fifth position. So the name is 5-ethyl, 5-ethyl, and remaining two substituents are same. What are those? Methyl. So at what positions they are present? Second position and fourth position. So 2, 4 dimethyl. Dimethyl, what is the root word? 7. So heptane. Heptane. So these are the main 5 rules we have to follow. So one is the longest chain rule. The second one is, so the next one is lowest number rule. Third one is alphabetical rule, and then equivalent rule, and the presence of different substituents. Total 5 rules are there. Just follow these 5 rules. So likewise, by following this, you can view. Okay. So in this, I think we get an idea about the IUPs nomenclature. Let us we practice IUPs in nomenclature on 2 examples. So 5 compounds I'm giving here. Just practice the giving the names to these 5 compounds. So likewise, 5 compounds, just try to give the names. So if there was any doubts, just give me a message in the WhatsApp, we will help you along. Next, move to the isomerism concept. So after the IUPs and nomenclature, we have to discuss isomerism. Isomerism. What type of isomerisms is alkanes can show? See, alkanes can show two types of isomerisms. So one is chain isomerism. Chain isomerism. And the second one is the special isomerism that only alkanes can show, that is conformational isomerism. Conformational isomerism. These two isomerisms that alkanes can show. Well, what about, first of all, what is isomerism? You may get that down actually. So isomerism is nothing but, see, a pair of compounds, two compounds A and B. They both are having the same molecular formula. So their molecular formula remains same. Molecular formula remains same. But their properties, the properties may be one is maybe different. Then that pair of compounds we call it as isomers. Okay. So what are isomers? The pair of compounds having the same molecular formula but showing the different properties. And the difference in the properties may be because of what, their structure, or maybe because of their orientation. So based upon that, isomerisms are of two types: structural isomerism, stereoisomerism. And under the structural isomerism, again 5 types are there: chain, position, functional group isomerism, tautomerism, open ring chain isomerism. So total 5 types of isomerism. Metamerism also there. So in that, the chain isomers, tell me what are chain isomers? See, chain isomers are nothing but a pair of compounds having the same molecular formula, but they differ in their chain skeleton. So same molecular formula, but they differ in what? Chain skeleton. Chain skeleton. Because of difference in their chain skeleton, they shows different properties. They shows different properties. And that pair of compounds we call it as what? Chain isomers. And that phenomenon is called what? Chain isomerism. So once again, the pair of compounds whose molecular formula remains the same, but they are differ in their chain skeleton. Because of difference in their chain skeleton, they are showing the different properties, and that pair of compounds are called chain isomers, and that phenomenon is called chain isomerism. See, chain skeleton, for example, if you take, but remember that to show this chain isomerism, minimum 3 carbons, minimum 4 carbons we need. Minimum 4 carbons we need to show the chain isomerism. Minimum number of carbons are how many? 4. Remember that. Okay. So if there was a 4 carbons, let us see. If all 4 carbons may be linear, so this is, what is the name of this one? Butane. The second compound, this is what? 2-methyl propane. So they both are having the same molecular formula, but they differ in the chain. Here the parent chain having 4 carbons, here the parent chain having 3 carbons. So because of difference in their chain skeleton, they both shows different properties. Okay, so minimum carbons required to show the isomerism, chain isomerism is 4 carbons. So there was a list. If the number of carbons in the compound is 4, how many isomers they can show? 2 chain isomers. If the number of carbons is 5, 3 isomers can show. 2 or 3 chain isomers. If the number of carbons are 6, it can show 5 chain isomers it can show. If the number of carbons is 7, 9 chain isomers it can show. And if the number of carbons are 8, that means after 8 carbons containing compounds can show 18 chain isomers it can show. If the number of carbons are 9, it can show 35 chain isomers it can show. If the number of carbons are 10, it can show total 75 chain isomers it can show. So just remember this list. So number of chain isomers based upon the number of carbons. If the compound having only 4 carbons, then how many chain isomers it can show? 2 chain isomers. 5 carbons, 3 chain isomers. 6 carbons, 5 chain isomers. 7 carbons, 9 chain isomers, and 8 carbons, 18 chain isomers. Okay, and then 9 carbons, 35, 10 carbons, 75. So likewise, what happened? Different number of chain isomers they can show. Next, this is what chain isomerism. Next, what is the second isomerism? They can show conformational isomerism. Conformational isomerism. What is a conformational isomerism? Conformational isomerism. See, conformational isomerism is nothing but the pair of compounds having the same molecular formula. Here they both are having the same molecular formula, but one compound, one isomer is changing into another isomer simply by rotating. And to explain that, we need some diagonal attestants. So let us assistants. So let us represent. Actually, the organic compounds we express in two forms. Two forms we can express. One is Sahars. Representation of organic compounds. That is, one is Sahars projection form. Projection form. The second one, Newman projection form. Newman projection form. What is a Sahars projection form and what is a Newman projection form? I am drawing the Sahars projection form and Newman projection form for the compound ethane. I am going to draw ethane. What is the structure of ethane? Ethane has two carbons. CH3 bond CH3. See, when you see the ethane along the bond, see, if you see this ethane here in this way, okay, then the Sahars projection form, the bond will be the inclined form. Here one carbon and here another carbon, and each carbon having how many hydrogens? 3 hydrogens, and those 3 hydrogens I am representing in 3 bonds, 3 lines. So this is what CH3. Okay, similarly, this is also having 3 CHs. Okay, so this representation we call it as what? Sahars. Sahars. So when we see the molecule along bond, so when we see the molecule along the bond, so this is what front carbon. This is a first carbon, and this is what second carbon. Okay, likewise we represent. This is what Sahars projection form. Newman projection form. Suppose when you see the molecule along the axis. For example, if you see this from this way. Okay, if you see this from this way, this is the first carbon or front carbon, and this carbon will be what? Back carbon. The front carbon always represented with a dot. Dot indicates what? Front carbon. In the front carbon, how many hydrogens are there? 3 hydrogens. And those 3 hydrogens, see, this is what? Front carbon. The 3 hydrogens I am drawing like this. 3 hydrogens. So this is a front carbon. Next, rear carbon means back carbon. Back carbon always we write it as a sphere. Okay, if you draw like a sphere, that is what? Back carbon. Even in the back carbon also 3 hydrogens are there, and those 3 hydrogens you just draw it from its circumference. Okay, so this representation we call it as what? Newman projection form, and this Newman projection form is we observe when we see the molecule along axis. Okay, always this dot indicates what? Dot indicates front carbon, and a sphere indicates what? Back carbon. So this is a representation of an organic compound in both Sahar's projection form and Newman projection form. Now let us see. Let us explain this conformational isomerism in ethane. Ethane by using a Newman projection form. I am going to use. So what are conformational isomers? So what I am doing? I am fixing front carbon. Fixing the front carbon. Okay, these are the 3 CH bonds present in the front carbon, and the back carbon. Okay, so this is the back carbon, and in the back carbon, the 3 CH bonds are like this. Like this. Here, the front CH bonds, these bonds, and the back carbon CH bonds, all are far away from each other. So, because of the far away from each other, what happened? There was no torsional strain, and this is most stable. And this most stable form, we call it as what? Staggered form. Staggered form. And this is what? Most stable form. The most stable form of ethane is what? Staggered form. Why they are stable? Because of no repulsions between front carbon CH bonded electrons and back carbon CH bond electrons. This isomer is most stable. Next, what I am doing? You just rotate this molecule. Rotate this molecule to 60 degrees. 60 degrees. Now just rotate this. Okay. Now what happens? You fix the first front carbon, fix it. Don't rotate this. You only change the back carbon. This is the back carbon. When you rotate it to the 60 degrees, what happened? This so in this case, the front carbon CH bonded electrons, back carbon CH bonded electrons are very, very close to each other. So there was a more repulsions between both of them. So this is a highly unstable, and this highly unstable form of ethane. This is, we call it as what? Eclipsed form. Eclipsed form. Okay, this is the staggered form, and this is what? Eclipsed form. So eclipsed form is what? Highly unstable. Why this is highly unstable? Because of more repulsions between them. So between stable staggered form and between highly unstable eclipsed form, there was a many number of conformational isomers are present. Many number. Okay, so those all isomers we call it as what? Skew isomers. Skew isomers, where the bond angle, see the angle between the front carbon CH bonds and the back carbon CH bond, this angle we call it as dihedral angle. Dihedral angle. So what is a dihedral angle in staggered form? Dihedral angle is 60 degrees. Okay, here the dihedral angle in eclipsed form, that is 0 degrees. What is the dihedral angle skew form? It is between 0 to 60 degrees. Between 0 to 60 degrees. So between eclipsed form and staggered form, we can create infinite number of isomers. Those all infinite number of isomers we call as skew isomers. So when you arrange the 3 types of isomers of ethane into the according to the stability, so which is most stable? So what is the order of their stability? The highly ordered, highly stable conformation isomer is what? Staggered. Staggered is most stable. After the staggered form, skew isomer, and the least one is eclipsed isomer. So this is what order of their stability. So staggered is most stable because of less repulsions. Eclipse is highly unstable because of more repulsions. Skew, the stability of skew isomer is intermediate between eclipse and staggered. Okay, so this is about the conformational isomerism in ethane. Now let us apply the same concept in butane. Let us apply the same concept in butane. See, if you take the butane, what is the chemical formula of butane? C4H10. C4H10, and the complete formula will be so. This is the complete structural formula of the butane. Now, for our reference, you consider these two carbons. These two carbons you take. This is the front carbon. Okay, this carbon is the front carbon, and this is the back carbon. In the front carbon, what are the groups are present? One methyl group, two hydrogens are there, and in the rear carbon, one methyl group and two hydrogens are there. So now let us apply the same conformation isomerism concept to the butane. So I'll draw the different conformation isomers. First conformation isomer I'm going to draw. This is the front carbon having one methyl group, two hydrogens, and this is back carbon having a methyl group and two hydrogens. And if you clearly observe the two bulky groups, what are those? The two methyl groups are far away from each other. So the isomer where the two bulky groups are far away from each other, that isomer we call it as what? Anti-form. In fact, this anti-form is a stable form. Out of all conformation isomers, this is the most stable form. Next, now you rotate this molecule to 60 degrees. 60 degrees you rotate. And after rotation, what happens? That is, you keep front carbon as it is. So that is CH3, hydrogen and hydrogen. Now you rotate this. So when you rotate the back carbon, this CH3 group is very, very nearer to hydrogen. Okay. And then here hydrogen, here hydrogen. Okay, so this is one form. And if you rotate this further 60 degrees, again we'll get this is CH3, hydrogen, and this is the back carbon. CH3, hydrogen. And you further rotate this to 60 degrees. Now this methyl group comes to here. CH3, hydrogen and hydrogen. And now this CH3 both are very close. This is the structure 4. And if you rotate this further 60 degrees, CH3, hydrogen, CH3, hydrogen. And if you rotate this further 60 degrees, finally, hydrogen. And this methyl group is again coming back to here. CH3, hydrogen. Okay, so likewise, different types of structures. Let us consider this is the structure 1, structure 2, this is the structure 3, structure 4, structure 5, structure 6. Total 6 structures are possible. Out of these all six structures, see, we clearly observe 3 staggered forms are there. What are the 3 staggered forms? If the dihedral angle is 60 degrees, then that forms being called as staggered form. So this is one staggered form, and here also this is one more staggered form. Structure 1, structure 3, and structure 5. So 1, 3, 5. These 3 are what? Staggered forms. Staggered forms. Next, structure 2, structure 4, structure 6. 2, 4, 6. These 3 structures we call it as eclipsed structures. And when you compare the staggered structures and the eclipsed structures, which are more staggered structures are more stable. But here 3 staggered structures are there. Out of these 3 staggered structures, in the first structure, the 2 bulky methyl groups are far away from each other. That is why, so that structure we call it as anti-form. So that is what we call it as anti. So the structure 1 is the most stable form. And in the remaining 2 structures, that is the 3 and the 4th structure. 3 and the 4th. You see that this is what third structure. Not 3 and 1, 3. This is a 5. 1, 1, 3, 5. The structure 1, structure 3, and the structure 5. These 3 are staggered. 2, 4, 6. All odd number structures are staggered. Even number structures are eclipsed. When you compare, staggered structures are more stable than eclipsed. And here, out of the 3, 1, 3, 5, first structure is the most stable because the 2 bulky groups are far away. That is why anti-form. This structure we call as anti. Anti-form is the most stable. Next, 3 and 5. In the 3 structure, third structure and the 5th structure, the dihedral angle is 60 degrees, and the 2 methyl groups are differentiated by the 60 degrees dihedral angle. They are not very close, and those 2 structures we call as Gaussian structures. Gaussian structures. These 2 structures we call as Gaussian structures. And after that, now come to the eclipse. Here, the eclipse, 3 structures are there. And if you see the second structure, and the 6th structure. In the second structure and the 6th structure, the methyl group is overlap on hydrogens. Methyl hydrogen. Even the 6th one also methyl hydrogen. So methyl hydrogens overlap. So that means they are not partially eclipsed. Second structure and the 6th structures are partially eclipsed. Whereas check the 4th structure, here the 2 bulky groups are overlap. So one or another. So because of when the 2 bulky groups are very close to each other, there was a strong repulsion. So this is a fully eclipsed structure. So after those structure, what is the next step? Partially eclipsed structures. Partially eclipsed structure. What are the 2 structures partially eclipsed? They are 2 and 6. Second structure and the 6th structure, they are partially eclipsed, and after that, fully eclipsed. What is the structure? Fully. So this is the order of stability in case of N-butane. So in case of N-butane, anti-form is in stable form. After anti-form, Gaussian form. After Gaussian form, partially eclipsed forms, and the least stable is a fully eclipsed forms. So this is what stability order. And when we draw the diagrams, point energy diagrams, such is all 4 different types of conformation isomers, we get the diagram like this. I guess. Now I'm going to draw the potential energy diagrams. potential energy. See, first of all, so first structure two, that is what Gaussian structure. After Gaussian structure, third structure, what structure will come? Partially. Third one is what a Gaussian. This Gaussian structure. Fourth structure, fully eclipse. Fully eclipse. And then again, fifth structure again, Gaussian structure. And the sixth structure again. Just partially eclipse. So this is partially eclipse. So partially eclipse, fully eclipse, partially eclipse, fully eclipse. So here, the graph will be like this. Here, stable form, that is not anti-form, anti-structure, anti. So anti-form has the least potential energy. Because of having the least potential energy, the anti-structure having most stability. As you know, what is the relation between the energy and the stability? Stability is inversely proportional to energy. If it is having the less energy, most stability. Out of this all, anti-form having the least energy, that's why it's the most stable form. After that, Gaussian, and here also Gaussian form. So the two Gaussian forms are coming next. Next, partially eclipse and fully eclipse. So this is the energy differentiation. And when you check the energy gap between Gaussian form and anti-form, this energy gap is 3.35 kilojoule. 3.35 kilojoule. And the energy gap between partially eclipse and anti-form, this is nearly 14.2 kilojoule. And the energy gap between fully eclipse and anti-form, this energy gap is nearly 18.4 kilojoules. So like there is the energy gaps are there. So if you go to the next book, you get a clear idea about this. So this is about the conformational isomerisms of both the ethane and butane. So I hope you understood this topic, conformational isomerism, very well. Next, let us move to the next concept, that is what preparation methods. So the preparation methods of alkenes. Methods of preparation of alkenes. If you see that, we can prepare the alkenes from different compounds. The first one is from alkenes and alkynes. From alkenes and alkynes. See, what is there in alkenes? Double bond. In alkynes, triple bond. So if we break the double bond and a triple bond, we get single bonds. So simply by how can we prepare? By catalyzed hydrogenation. Hydrogenation. What do you mean by the hydrogenation? Addition of hydrogen. That is what we call as hydrogenation. In the presence of catalyst to do the hydrogenation, that is what catalytic hydrogenation. So simply by the catalytic hydrogenation of alkenes and alkynes, we can prepare alkenes. Let us take a few examples. Here, what is the catalyst we use? Catalytic hydrogenation. So what is the catalyst we use here? That is in the presence of platinum, palladium, nickel. In the presence of any one of these catalysts, if you add hydrogen, so then this process we call as catalytic hydrogenation. Now I'm going to explain this by taking an example. You take ethene, CH2, double bond CH2. Take ethene. So this you add hydrogen. In the presence of platinum, palladium, nickel. You can take anything. And the normal room condition only maintain, no problem. At normal room conditions, if you add hydrogen in the presence of this catalyst, it can undergo, no problem. So ethane. Now what happened is one of the bond will break down and then it gives ethane. So ethane gives ethane. Ethane. So that is one example. Otherwise, you take alkyne now, CH triple bond CH. To this, add hydrogens. Hydrogens. In the presence of platinum, palladium, and nickel. Okay, at normal room conditions, 2 for 25 degrees. Then what happened here? Total 3 bonds are there. Out of 3 bonds, 2 bonds now it will break down. So finally, we will use CH3, CH3. So yeah, this is what ethyne, also we call as acetylene. Acetylene gives what? Ethane. So alkenes and alkynes, by doing cation hydrogenation, we get alkenes. Here, 2 points you should remember. You have to remember 2 points here. What are those? If you do the cation hydrogenation of alkenes and alkynes in presence of nickel, we call it as, okay, cation hydrogenation in presence of nickel. In presence of nickel is what we call as Sabatier Sandran's equation. And one of the main reaction. What is the Sabatier-Sandran's equation? If you do the hydrogenation in the presence of especially what catalyst, nickel catalyst, then the reaction we call as Sabatier-Sandran's reaction. That is one point you have to know. And one more point. The addition of hydrogen to the alkenes follows. It follows. Hydrogenation follows syn addition. Syn. So 2 types of additions are there. Syn and anti. Syn means if you add the hydrogens in the same set of the double bond, then that is called syn addition. So let us take hydrogens to the same. That is what CH3, CH. Here this example is not clearly explained. Let us take C double bond C, CH3, CH3. Likewise, I have taken. Now you add hydrogen. Now these 2 hydrogens are adding in the same side of the double bond, so that we are getting CH3, CH3, H2, H2. So this is what syn addition. So addition of hydrogens done in the same set, that is called syn addition. So while in the syn addition, suppose the given compound is a cis isomer. We will get always meso compound. We will get. Okay, cis isomer always use meso compound. So I am giving an example. C double bond C, C2H5, C2H5. So to this, I am adding hydrogenation in presence of platinum or palladium and acid to enhance it. Then we will get okay. So this is what a meso compound. What is a meso compound? If one half is a mirror image of another half, then that is called meso. So if it is a cis compound, it will use meso compound. If the given compound is a trans, suppose if the given compound is trans 1, if they undergoes syn addition, it gives racemic mixture. So just remember this point. Cis isomers gives meso compounds, trans isomers gives racemic mixtures. So this is about the catalytic hydrogenation of alkenes. So this is the first method. So next move to the second method of preparation. Okay, next move to the second method of preparation. Second method from alkyl halides. From alkyl halides. What is the alkyl halides for Rx? Alkyl halides general representation is Rx. So when the from alkyl halides, in two ways we can prepare. In two ways. One way is by reduction. By reduction of alkyl halides we can prepare. And the second one is by one of the most important famous reaction, that is what Wood's reaction. By Wood's reaction we can prepare. Okay, so these are the two ways we can prepare from alkyl halides. Okay, so the first one by reduction. How can we prepare? By using some reducing agents. Reducing agents. Reduction means addition of hydrogens or removal of oxygens in the presence of reducing agents. That is called reduction. Let us take. I am taking alkyl halide. I am doing the reduction in the presence of reducing agent. In the presence of reducing agent, it will do. What happened? Now this bond will break and hydrogen is adding to both sides. So alkyl halides, alkyl group is coming out as Rx, RH, and halogen is coming out as HX. Here the question is, what are the reducing agents we use? See, we can use the following reducing agent: zinc in the presence of HCl, or zinc in the presence of acetic acid, or lithium aluminum hydride, or sodium borohydride, or triphenyl arsenic hydride. So any one of these 5 reducing agents you can use. Okay, zinc in the presence of HCl, zinc in the presence of acetic acid, lithium aluminum hydride, sodium borohydride, triphenyl arsenic hydride. In the presence of any of these reducing agents, if we add hydrogen to the alkyl halides gives alkanes. So this process we call as reduction. But one point you have to remember, especially these three. So first of all, lithium aluminum, if you take lithium aluminum hydride. Lithium aluminum hydride, primary alkyl halides or secondary alkyl halides. If the alkyl halide is the primary or secondary, they comfortably use alkanes, no problem at all. They use alkanes comfortably. But if it is a tertiary alkyl halides, okay, so then they undergo elimination. Elimination dominates, so that we are getting alkenes. So we cannot prepare the alkanes from tertiary alkyl halides by using lithium aluminum hydride. Next one.
Wait, problem here, sir.
Okay, so lithium aluminum hydride. By using lithium aluminum hydride, primary secondary alkyl halides can easily use alkanes, but tertiary alkyl halides cannot give alkenes. Instead of alkanes, they use alkenes. Next, sodium borohydride. If you use sodium borohydride, secondary or tertiary alkyl halides can use alkanes. There are secondary, tertiary alkyl halides can use alkanes, but primary alkyl halides they doesn't use alkanes. They doesn't use alkanes. So that is one more point. And whereas triphenyl arsenic hydride, they can convert all primary, secondary, tertiary alkyl halides into alkanes. So that is the likewise the different reagents gives different products, especially during the preparation of alkanes from alkyl halides. So remaining Woods reaction, and the other methods from salts of carboxylic acid by Woods electrolytic method and from Grignard's reagent. So how to prepare and everything tomorrow we will continue. So until then, take care. Thank you.
Students, stay online. Next math class will be starting.